Okay. No one's here, but I promised I'd do the recording, so we'll go through some examples. If people come late, arrive in this meeting, then I will then take questions and we can look at those. My material is partly in Finnish, but I'll translate it into English and then we'll talk about that a little bit. I haven't had time to translate it all to English yet. Work is going really slow. So I thought in the first moment I'd share this one comic which I like. So with this quarantine measures in place, I think we're quickly approaching a situation where you don't have to wait for 1 month. For me, the degradation is already somewhere between the 6 month and 1 year in. English speak is becoming hardness, yes. Not yet at the kind of a completely how should I say, I'm not yet completely out of social skills, but quickly approaching, yes. All right, let's go to the actual material here now. Let me just take that examples file and share it for you. Right. Zoom in a little bit. Sorry though. Okay. Now we're ready to do that. Okay, so here we have this situation of a game. Players need to play. Players are playing this game where there are 3 routes to reach a goal. Only one of these 3 routes is successful, and the game is played by 2 teams. Each team has 3 players, and they can split the players in any way they like among these 3 routes. Sorry. We have Team A and Team B. Team A's strategy is to play it safe, so they send 1 player on each of the routes, and Team B chooses players randomly. So each player picks a random route independently of the others. So that means that the correct route for Team A is chosen by exactly 1 player, and the correct route is chosen by Team B by a random number of players, the randomness here being each player has a 1 in 3 chance of picking the right route. So that means it's got binomial distribution. Remember, it's for each player, it's a Bernoulli choice. Choose either the successful route or not. And a successful route is chosen with probability 1/3. And a repeated Bernoulli experiment results in a binomial distribution. So we have a situation where we have a binomial distribution with n equals 3 and p equals 1/3. The rules of the game stipulate that there is a 12,000 euros reward that is split between all the players who reach the goal, and that this money is awarded to the whole team. So if only 1 player reaches the goal, then their team gets the whole 12,000. If 2 players from different teams reach it, then it's split in half. And then, the number of players, it's split in terms of how many A players and how many B players got there. So the proportionate number goes. So here's another example. If 1 player reaches, if all the B players choose the wrong route, then choose a wrong route, then all the 12,000 go to the A. But if all the B team players get there first, so get there, and only one A team player gets there, so it's split 3-1. So team B gets 9,000 and team A gets only 3,000. So we should calculate the expected winnings of each team and which team has the better strategy. So the expected winnings are symmetric. So if B has expected winnings of €, if team B has expected winnings of X euros, then 12,000 minus X goes to A. This is a rather fundamental situation. The expected values must add up to the whole prize money. So we can, oh, sorry, I didn't mean to put that notation there. So it's clear that exactly one player in team A reaches the goal. On the other hand, team B player each has 1/3 probability. So we have this binomial distribution, which I already explained, and we'll make a table out of this. So there's 0, 1, 2, or 3 players reaching from team B, and what is the probability and what are the winnings? So we calculate the probability. The probability that 0 players get there, that's 3 choose 0. There's only one way to choose 0 from 3. 1/3 to the 0, that's 1, times 2/3 to the 3. So that's 8/27. So in 8 cases out of 27, team B gets nothing. On the other hand, there is a 4 in 9 chance of one player from team B reaching the goal. It's 4 out of 9 because that's 3 choose 1. So that's 3 times 1/3 times 4/9. So 3 times 1/3 equals 1 times 4/9. So that's the 4/9. And then winnings in this case would be 6,000. And 2 players reaching a goal, that's 3 choose 2. And then 1/3 to the power of 2, so that would be 1/9. That 3 choose 2 is 3, so we get 2/9 as the probability. In this case, there are 3 players reaching the goal, 2 from team 2 from team B and 1 from team A. So the winnings amount to 8,000, 2/3 out of. The extreme case where all the players choose the same and correct route is there's just one way of choosing that. That's 3 choose 3. 1/3 to the 3. That's 1 in 27. And in this case, the winnings are 9,000. So if we calculate the expected value of the winnings here, well, this obviously doesn't, the 0 factors out completely. And then we get 6,000 times the probability of getting 6,000 plus 8,000 times the probability of getting 8,000 and 9,000 times the probability of getting 9,000. And that's 4,778 euros winnings expected value. The winnings are split, so the expected winnings of A must be, 12,000 minus that. So obviously the team A strategy is better. So this is team A follows what is called a hedge strategy. So there is some sort of random element in this game. If both teams chose the same strategy as A, this is a review question for you. What would the expected winnings be? Well, obviously, if both choose exactly the same strategy, then we don't even need to care what that strategy is. The expected winnings of both must be the same. We're not going to go into the theory of games here, but the theory of game theory is a very fascinating branch of mathematics, if you will, or branch of, how do you say that? I think it's branch of mathematics. it has a wide range of applications, and it's for instance got applications in economics and all that. And here the idea is that the strategy that is chosen, if the both players, both teams have the same strategy, then they're going to have the same winnings. And the thing is that there is a thing called Nash equilibrium here, meaning that it's a strategy where there is no both players choose a strategy such that no matter that if the other player chooses anything differently, then they may get a better result, but then this player may get a Nash equilibrium is a strategy where neither player can change the strategy in order to win more. An example of this is probably, I haven't analyzed this from that perspective, but I think Team A strategy is an equilibrium strategy, so there's no way to beat that in this game by any scheme of randomness if you don't know which of these three. That's a falls out of scope for this, but you know, if both players choose the same strategy, then obviously the winnings are split, but in here the A strategy dominates over the B strategy. Doesn't mean necessarily that in all games this A strategy is the one that you pick. For instance, if you're playing a game where you are losing and you really need, I mean, you're going to lose if you get the same amount as the other one, but you need, if you get 9,000 and the other one gets 3,000, then you win, if that's the only way for you to win. Then this strategy gives you at least 1/27 chance of winning, whereas if in the case of split winnings, if you lose a bigger game, then the move here would be bad, because then you don't have a chance of winning if you choose the same strategy so it's all depends on. But I'm digressing, and this, fascinating as it may be, is not a topic for this course, so let's move along. The second question was very common situation for probability calculus courses. Assume that people's birthdays are uniformly distributed over 365 days of the year. We assume that no leap year is in question. Let's assume that now. And suppose a room has 200 people. Oh, sorry. What is the probability that today is the birthday of? Well, in A case, no one. And B, exactly one person, or C, 2 or more people in the room. Well, let's calculate that. Today, we first of all, let's notice that, because let's assume that there are 2 people coming in, 200 people coming in. Each has the probability 1/365 to have a birthday today. So we can model the number of birthday persons as having a binomial distribution with parameters 200 and 1/365. So we calculate the probability that no one has, and I use the calculate. Oh, sorry, I'll have to fix that. There's a typo there. Just 1 second. As you can see, I was working on this late at night and morning today. So even though I have the model answers, what I have been doing is I've been translating them, and sometimes when I do the translation, there's a slide. Okay, there you go. So the probability that there is no one with a birthday, this binomial distribution, so 200 choose none, that would be just 1 times then 1/365 to the power of 0, which is 1. So the only thing we have left is to calculate 364 over 365 to the power of 200. And it turns out that that's roughly 0.578. So I took this from the model answer. So let me calculate this with my calculator here. So we have 364 divided by 365 to the power of 200, and it's 0.57770, so that's 578 roughly. Yeah, that's true. Okay, good. And another typo there. Why did I make that same mistake there? I'm missing in LaTeX. I mean, the good thing about it is that when you see something here, you can notice that it's obviously birthday for one person must be lower than the probability of birthday for 0 persons, because 0 already was over 0.5. So over 1/2 probability. 200, choose one, that would be 200 times, well, 1 over 365 to the power of 1. So that's 200 over 365 times 364 over 365 to the power of 199. So we get, it turns out it's 0.317. 0.317 being the probability of exactly one person having a birthday. Now, the third question was 2 or more people having a birthday, and now we've actually already calculated everything that we need, because we know that the probability of 0 persons having a birthday today, and the probability of 1 person having a birthday today. So probability of 2 or more is just the rest of the probability. So that's just 1 minus whatever is left. There's a parenthesis missing there, which I'm going to add now. There you have it. So probability of x is greater than or equal to 2 is 1 minus the combined probability of x being 0 and x being 1. And we calculated those, so we get roughly 0.105. Here, the thing is, if you now consider these numbers, they're relatively small. Now, I have another question for review. You may know this by the name, it goes by the name of the birthday paradox. The birthday paradox being, what if we were to calculate what is the probability that some 2 people in this room have the same birthday? And that probability is very high. The probability of 2 people having the same birthday is very high. Do you know why? Can you guess? Well, the reason is today is only 1 day out of 1 of 364, 5, sorry. But the more people we have, the fewer days we have left for the other people to have a birthday, so that no 2 people have a birthday. So if you have 1 person, obviously that person has 1 birthday, so there can't be 2. The next one will have 364 over 365 probability of having a different birthday. But then the third person has 363 days left, and then the fourth has 362, and so forth. So instead of having this 364 over 365 to the 200 there, we have this number diminishing. And when this diminishes and we multiply those together, then the probability starts going down pretty rapidly. The probability that there are no 2 people with the same birthday. check it out. It's very, very low for 200 people, the probability that no two people in this room have the same birthday. So whereas it's pretty probable that no one has a birthday today, I mean, surprisingly, think about it, 200 people. And 365 days. You'd kind of expect, I mean, the expected value of people having the same birthday today, having the expected number of people having a birthday today is 200 over 365. However, that's just the expected value. The variance is very, very high, right? So on average, about what's that, 200 over 365, what's that? That's 0.6 people have the same birthday. Roughly 0. Oh, let me just calculate that for you. I'm not very good at doing mental maths, by the way, as you've probably noticed. So 0.56 people roughly have a birthday today on average. Still, it's more than that. The probability that not one of them is today is 0.578, but that's how expected values work. There's a large tail here. I mean, very, very small probability that there is like 100 out of these have a birthday today. It's still possible, and the small probability there, tilts the expected value a little bit further. So even though 0 and 1 are pretty dominant here, I mean, count for what, 80% of all the probability mass? Close to 90. Sorry, I'm eating my morning porridge while I'm talking. This is really rude, and I've lost my social skills due to this distant. Anyway, let's move on. Here's a question. I'm going to show that. So an airliner has 2 and 4 engine aircrafts. An aircraft can fly if at least half of its engines are functional. Let's say that the engine has a probability of 0.6 of working through the whole flight. This is ridiculous. Obviously, that it's much higher than that, but let's just assume. Possible engine failures are independent. What kind of aircraft is more likely to make the whole flight? So, aircraft can fly if half its engines are functional. So we're looking for let's call it X and Y, X for the 2-engine aircraft and Y for the 4-engine aircraft. These are the number of functioning engines. So for X, it's a binomial distribution with 2 and probability of 0.6 of functioning. And Y, it's a binomial distribution with 4 and 0.6 probability of functioning. However, the 2-engine aircraft flies if X is greater than or equal to 1, and the 4-engine craft flies if Y is greater than or equal to 2. So now, probability that X is greater than or equal to 1 is 1 minus the probability that X is 0. So we can easily calculate this. It fails at 0.4 to the power of 2. Both are failed. So that's 0.16. So 1 minus 0.16 is 0.84. That's the probability that the 1-engine aircraft can fly. On the other hand, the probability that so there's a lowercase y. Sorry about that. I'll fix that. Where is it? Where is it? Over there. I'll fix that. Just a second. And now it's fixed. So the probability that y is greater than or equal to 2 is 1 minus the probabilities 1 is smaller than or equal to 1. So you have to subtract both the 0 case and the 1 case. And in this case, I used a calculator. So we get 0.82. So in fact, the 4-engine aircraft is less reliable. It's got more engines, but because half of them must be functioning, then it's less reliable because it fails after 2 failures out of 4. So this seems a bit counterintuitive, doesn't it? I mean, you have a more than 50-50 chance of the engine working. So you kind of think that if you add more of these engines, then it's probable, it's more likely that things work out if there are more engines. But no, that's not the case in this case. So let's look at this. I mean, B was the extremal case where P is equal to 0 or P equal 1. Both have the same security rate. I mean, if it's 0, then neither of them will ever fly. And if it's 1, neither of them will ever fail. In between, there is a third value for when this P happens. In fact, we can guarantee that this must happen because, they are equal at 0, they're equal at 1, and they're not equal at 0.6. One is larger than the other, so at some point it must become larger than the other, and then also at some point it must become smaller than the other. Well, not necessarily, it could be, but in this case it will. So let's look at that. Assume then that they have the same P here, and X is binomially distributed with 2P and Y with 4P. And we look for a value of P such that P probability of Y greater than or equal to 2 is the same as probability X greater than or equal to 1. So we, on the left-hand side, we have here the probability that Y is greater than or equal to 2. So that's 1 minus probability of Y equal 1 and minus probability of 1 equal 2. And here is the probability that X is 0. Y equals 0 and Y equal 1. Yeah. Okay. Now we calculate these. This comes out at 1 minus P to the 4. Everything else here is 1. This comes out at 4 times P times 1 minus P to the 3 here. And then this comes out at 1 minus P to the 2. We move everything to the left-hand side. We take 1 minus P squared as a common multiplier. Then we can rearrange this. If we see here's a minus 1, if we write this one out, it becomes at 1 minus 2P plus P squared. So the 1 will cancel this one here. And then this comes out at 4P minus 4P squared. So that results in minus 3P squared because here was the P squared and here the 4P squared. So minus 3P squared and here the plus 4P and here the minus 2P, and that results in 2P. And here we can take P from here as a common multiplier. So we get this 3. So either this is 0, this is 0, or this is 0 because it's product of 3. This comes out at p equals 0. This comes out, p equal 1, and this comes out at p equals 0. So this comes out at p equals 2 over 3. So we see that at probability 2 over 3, 4-engine aircraft is more reliable. And from this point onwards, as P grows, P becomes larger, then the 4-engine aircraft becomes more reliable. We are kind of leveraging the fact that the failure rate is very small, so we can add a lot of engines, and it becomes less and less likely that that half of them fail, the more there are, because NP is the number of failures on average, and then there's the. All right. This sort of analysis in reliability analysis is often very good idea to make. I mean, if you are trying to make some using the use of redundancy to make something more reliable, and if failures can be considered as independent, then you have to analyze how much redundancy is in fact beneficial. It depends on the failure rate. All right. And the mode of, what kind of number of failures leads into catastrophic failure. This goes on to all kinds of things that you need to plan, like healthcare system or something like this. I mean, it's unlikely that many people get sick at the same time. So it's not. We can't have. If we have hospitals, hospital beds, the number of hospital beds is if it's so that on average most hospital beds will be empty, then you're wasting a lot of this resource. Your upkeep cost for these hospitals is larger than it needs to be. On the other hand, if you're working on average, if you're very often working at close to capacity, then when there's a big epidemic that needs, where a lot of people need hospitalization, then the hospitals are quickly overwhelmed. So you kind of have to figure out what is the probability and how much catastrophic situations can you tolerate. We are seeing this in different countries now over the world. I mean, there are other different issues that are affecting this, but really, I mean, probably these are not, you don't use binomial distributions there because the n's are terribly large and so forth, but maybe you use Poisson distribution or something like that. But let me warn you again, a particular distribution is such that it's usually not very reliable when it comes to unexpected catastrophes or unexpected situations such as pandemics or natural disasters. Many countries and many regions where there's a lot of frequent disasters, if you will, they suffer much less with great natural disasters and this than those places where they are rare but still happen. So, for example, Japan has a lot of earthquakes, but whenever there's a huge earthquake that hits Japan, it's usually not that big a deal, except the one with the tsunami, which was kind of unexpected. Another being snow. I mean, Helsinki airport is hit by snow several weeks per year. Heavy snowfall comes around at, dozens of days a year. The last time Helsinki airport was closed because of heavy snow, I think it was in 1997 or something like this. I don't remember. Whereas Heathrow Airport, one that you'd expect to be very resilient because it's one of the busiest airports in the world, is snowed in a couple of days almost every year. and there's far less snow there. But the thing is that if they have the same level of preparedness, then it costs money. So now they lose a couple of days. It's very expensive per year, but it's more expensive to have that equipment to get rid of the snow. Whereas in Helsinki airport, if they don't have that equipment, then 1/4 of the year the airport is useless. So that's much more expensive than the equipment needed to handle it. So here's the thing about probabilities: you have to factor in the situations as well. And this is a very rudimentary analysis of this, but that's the sort of application that I hope that when you study further this topic, you will learn. All right. Number 4. We have 10 boxes. Each is a very, very large number of marbles. The numbers are equal. So let's say that they have 1,000 marbles each, or 10,000 even, very large. Large enough so that when you pick one, you don't notice any real difference. Four out of these 10 boxes have red marbles and 6 have blue marbles. Person A chooses 5 boxes at random and picks 1 marble out of each. Then, let's say that person A puts the marbles back, or there's so many marbles that it doesn't even matter if they put it back or not. Then a person B takes all the marbles and pours them into one big box and picks 5 marbles at random. We're assuming that they get properly shaken and stirred. So which one of these has the larger probability of picking 3 red and 2 blue marbles? So this is the answer. So first of all, person A will follow the hypergeometric distribution. There are 10 boxes, 4 reds, and 5 picks in total. So 6 non-reds. So the hypergeometric distribution gives us, you choose 3 out of the 4 boxes to get the 3 reds, and 2 out of the 6 boxes to get the 2 blues. Okay, that's the number of ways you can pick those. And the number of total ways you can pick is you pick 5 out of 10. And when we calculate this, comes out at 5/21, which comes down to 0.2381. It's about 23.8% chance. Right. But what about B? When B takes all the marbles and pours them into one box, then each marble has a probability of coming out at red or blue. And there are 4 out of 10 of these marbles will be red. So you have a 0.4 probability of picking a red marble separately. And assuming that it's well mixed up, then and the number is so large that we can think of this as a binomial distribution. 0.4 chance of each of them marbles being red. So we pick 5, and we're looking for the probability that the x is equal to 3. So that's 5, choose 3 times, then the number of successes is 3, so 0.4 to the power of 3. Number of failures being 2, so that's 0.6 to the power of 2. And we get, after this, punching this into a calculator, we get 0.2304. So that's 23% chance. So person A has a slightly higher probability here. So you see the hypergeometric distribution and the binomial distribution are well, they're quite different in this case. Similar but quite different. Different results, somewhat different. All right. At this moment, I would ask if there are any questions, but for some reason, I'm not getting any participants here. Let me go to this number 5. So we have a text that has printing errors occur randomly. So text, this is a bad translation. Let's say that we have a printer that has printing errors occur randomly, 30 errors per hour. What is the probability that within 6 minutes there are no errors or there are at least 2 errors? So I'm saying here that it's Poisson distributed, but let's consider this why. Why is it Poisson distributed? Why can we consider it a Poisson distribution? So here's an interval, an hour given, and there's a number of events, errors, 30, occurring per unit of time. That's an hour. We say that these errors occur randomly, but what do we mean? Let us recall. There were 3 things that need to happen. It's a fixed number of errors that happen, or fixed number of events that happen, random being, of course, but an expected number of events that happen in a certain time interval, and then it's independent of the time at which we look at them. So in every hour, we get 30 errors, and we assume that that's the way it goes. Also, the probability that it happening at very, very short interval, many times over, is 0. So it's, let's say that these are so random that it's very, very unlikely that 2 of these errors happen when printing the same letter, for example. So let's assume that, and we assume that, well, that's actually it. There were 3 assumptions. At different time intervals, the errors occurring are independent. It's a constant a probability within a unit of whatever it is that they're measuring, here the unit of time, and that the probability of them happening at a very short interval many times is approximately 0. We can use the Poisson approximation. So per hour, that's 30, and we have 6 minutes, 60 minutes in an hour, and so 6 minutes would be 6 minutes would be 1/10 of that hour. So we'd expect there to be 3 errors every 6 minutes, 1 every 2 minutes, if you will. Assuming they have a Poisson distribution, so x not equal. That's again another typo. Let's go fix that. It should not be the equality sign. It should be x. I'm usually very particular with this. But I do make printing errors, if you will. So the probability that there are none, we get it from the Poisson distribution. So that's lambda to the power of k over k factorial times e to the minus lambda. Lambda here being 3. So we get 3 to the 0, which is 1, 0 factorial, which is 1. So we get e to the minus 3. The probability that x is equal to 0 is 0.0498. The probability that there are at least 2, well, that's the probability that there is not 0 and not 1. A 0 comes up, well, each one of these, again, there's a missing parenthesis. Man, I do make these mistakes a lot, don't I? Okay, that should be fixed now. And that is, there it is. So 3 to the 0 over 0 factorial, that would be 1 plus 3 to the 1, that would be 3 over 1, that's 3. So that's e to the minus 3 times 4. And it comes out at 0.19915. And we take 1 minus that, so that's about 0.801. 0.801 probability of having at least 2 errors. So it's pretty high probability. We have 3 errors on average. That's the lambda, so it's the expected value is 3. And it's very high probability that we have at least 2. Okay. I'm checking that there are no participants still. Well, I'm going to go through one more question. The probability to hit a target with 1 shot of a gun is 0.02. What is the probability that out of 100 independent shots, at least 3 hit the target? So here we have a small probability and a high number of repetitions. So we can use either a binomial distribution or we can use the Poisson distribution as an approximation, because if n is large and p is small, then we can do this. So let's do it first with the binomial distribution. We get probability, oh, there's again, a typo. Sorry. I'm glad this goes on record to show how many mistakes I make. So maybe you will be able to relax a little bit. So the cases where x is smaller than 3 are in fact those that where x is smaller than or equal to 2. So I didn't bother to write this in more detail. So I have to calculate 1 minus, and then there's the probability that x equals 0. That would be just 0.98 to the power of 100. And the probability that x equals 1, well, that's 100 times 0.02. So that's what, 2 times 0.98 to the power of 99. And then 100 choose 2, not even going to calculate it in my head, times 0.02 to the power of 2 times 0.98 to the power of 98. Add those and subtract from 1. And I punched it into calculator, I get 0.3233. So we got about 30% chance of hitting 3 or more targets if we have a 2% chance of hitting 1, and when we hit it 100 times. The expected number of hits is 2, right? 0.02 times 100, that's 2. And I could write here, the parameter here is lambda is 100 times, so that would be 2. I'm going to just write that. And the probability is 1 minus the probability of x being 0, x being 1, and x being 2. And so the first one is always 1. There's only one case, x equals 0. That's 2 to the 0 over 0 factorial. That's 1. This is 2 to the 1 over 2 factorial. Sorry, 2 to the 1 over 1 factorial. That's 2 over 1, that's 2. This is 2 to the 2 over 2 factorial. 2 to the 2 is 4, 2 factorial is 2, so that's 2 again. And every term here has a multiplier, e to the minus 2. And we get 0.3233. So we get up to the 4th digits, we get the same result. And that's what you would expect. You would expect that once there are, once n is very large and p is very small. Okay. a good rule of thumb, you know, and that's not, but the Poisson distribution works pretty well if n times p is a relatively small number between, let's say, 1 and 10, and n is, let's say, high tens or hundreds, and p is somewhere in the, you know, 0.0 somethings. And if n is larger or p is smaller, then that's fine. But roughly so that the n times p is a couple of orders of magnitude smaller than n, and a couple of orders of magnitudes larger than p. In this case, that's it's 1/50th of n, and about 100 times bigger than p. Obviously, it's 100 times bigger than p because n is 100. And this is a very good situation. All right. Let's carry on. I haven't yet translated that 7, so I'm going to skip that. I'm going to go straight to 8. So because this is normal distribution, you need practice in normal distributions. Okay, so device has a lifetime of X years, and we assume that X is the normal distribution. There are 2 types of devices. Type A has 27 months, and type B has 30 months of expected lifetime. The models that I had a typo here. Sorry about that. The standard deviation for A is 5 months. In my example, in the previous example, it was 4 months. It doesn't change anything except the numerical values, and I had calculated and verified those results only for the numerical value 5, so I changed it back here. I could have done it by hand to calculate it with the 4, but you know, you're going to be looking, I mean, based on the fact that no one is here, I'm guessing that everyone will just look at the model answers and maybe look at this video. It's not the recommended way of learning, but what am I going to do? What am I going to do? I mean, if you don't do it beforehand, then, you know, it's not my problem. I mean, I do recommend you do that, but still. Okay, let's go. I see someone arrived here. Nice. Welcome. I think, yeah, the example sessions, I'm not sure if people got my message. Regarding this 9 o'clock. Did I not mention it at 9 o'clock? It seems like I did not. It seems like people are expecting it to be. Yeah, I didn't mention. Yeah, that's true. Yeah. I think I mentioned it at yesterday's lecture. I think I did mention that we get, not yesterday's, on Wednesday lecture, that we convene at 9 o'clock on Friday, but I don't think, yeah. I think the message was lost. That's my bad. Sorry. Yeah. I will probably, yeah, well, there's not much I can do now. I have another meeting coming at 10:30, so that's my problem there. Yeah. Sorry about this, definitely. Let's go through this number 8. So the question is, which type would you choose if you need to maximize the probability that you can use the machine for at least 30 months? There's one way to do this A, which doesn't involve any calculation whatsoever. If you know that the type I has, both are normally distributed and A has the lifetime of 27 months. So what do you know? You know that the probability that it lasts at least 27 months is exactly 1/2, because normal distributions are symmetric. So you know that it's a 50-50 chance of getting past 27 months. So whatever the probability of getting past 30 months is, it's going to be strictly less than 0.5. On the other hand, you know that B has expected lifetime of 30 months, and it's a normally distributed variable. Because a normal distribution is symmetric, then you know that it's exactly 50% chance of reaching 30 months. So that's why question A, you don't have to calculate anything. You can use this to justify that A has a shorter lifetime, expected lifetime shorter than 30 months, so it's got less than 50% chance of reaching 30 months. So B is better. And that's legitimate, and that's fine. Oh, so but just to be sure, I calculated it here. We have to compare these, normalize the A into 0, 1 variable. So we do it here. So the probability, we first of all notice that the probability of it being at least 30 months is 1 minus the probability of it at being at most 30 months. And here we do this, we get the Z value, or the Z, which is 0, 1. So we subtract 27, divide by 5, subtract 27, divide by 5 from 30. So we get Z is smaller than or equal to 0.6. And this either by use of software or looking at from a table, we get 0.7257 for the probability that Z is smaller than or equal to 0.6. And then this complement comes out at probability 0.274. So it's pretty much worse. I mean, you got only 27% chance of having it last for 30 months. The situation becomes radically different if you need to use it for 36 months. Then what kind of a device would you choose? Well, both are more than likely to break down before 36. Oh, okay. I'll switch. I have the Finnish one here. That's one I was. So let's switch, and I'll share this other one. So in here, I mean, this is the Finnish one. I'll just explain this in English. So in here, this is the first case scenario. We see that the distributions look like this. That's your distribution for the B, and that's for A. And now we ask the probabilities of XA being greater than 36 and XB being greater than or equal to 36. So we calculated for A at first, 1 minus XA smaller than or equal to 36. We normalize here the same way. We get here Z smaller than 1.8. And calculating that, it comes down at 0.0359. So it's got about 3.5, just over 3.5% chance of lasting for 36 months. But for B, it gets even worse. I mean, here, probabilities, calculating these probabilities, this comes out at Z smaller than 3, considerably larger number than here. So we would expect this to be smaller. So we get 0.0013. So this 0.1%. So this is worse by a factor of almost 30. Now, I'm not going to claim this, I'm not going to make this claim to hedge my sayings here, because Larry Summers got fired from the position as a president of I think Harvard, because he said this. But I'm just going to use what he said as an example. So he tried to explain a very inflammatory claim that the reason that there are more men among top researchers and top scientists and whatever in certain fields has less to do with the discrimination and more to do with the fact that the distributions of talent, or what you might have, and mind you, I'm not claiming that he was right, I'm just saying this is what he was saying, resembles somewhat these curves. So we see that women and girls tend to do better at school on average. But we also see that whatever it is among boys and men that causes this how well they do in school, it seems to have a wider distribution. So variance of these, whatever you call it, abilities or whatever, in boys and men seem to be greater than that in women. So his claim was that men and women, in terms of their talent and tenacity and whatever the qualities are that make you make you good at doing research or whatever he was talking about, has a different kind of distribution. And his claim was that female students and female researchers have a higher average but a lower variance. So they resemble something like these two curves here. But then when you look at the top researchers, then you're not talking about those that are in the mid region. You're talking about those people who are at the further regions of those distributions. So you're looking at this part here where the curves are almost flat. And if you zoom in here, you notice that once you get to this let's zoom in more. Let's zoom in even more, sorry. I hope this is visible. So when you zoom in here, you notice that this curve that started out from higher above, then you got to the very edge, it goes lower here, and then there's a higher proportion of these. If you look at the whole population and averages, this curve is the curve of those who do worse. But when you look at this region here, where there's a very rare events to begin with, then these are far more higher probabilities. So whether or not he was correct in his claim, I'm not making any claim as to whether he was right about his claim. I'm just saying it was not nonsensical if you take into consideration the fact that there seems to be greater variance in some populations than another. It doesn't mean, anything. I'm just saying people should be aware that if things are normally distributed, then the averages may matter less than variances or standard deviations if you are talking about a very small subpopulation. And this doesn't mean just men and women, or it doesn't mean just any group of people. It can mean a lot of things. If you're choosing from a large body of devices, a large body of animals, a large body of people, whatever it may be, then if you are choosing from a very large group and you are able to choose a very small proportion, then sometimes the variance matters more than the average and the expected value. This goes in optimization very well. I mean, let's say that you are running optimization algorithm in a situation where you are employing randomness. You're generating um, random outcomes, and the problem is so irregular that it's hard to use any intelligent means. So you're just shooting points and trying to figure out which ones are the more promising ones. Then shooting them far and wide, you know, to regions that don't look promising, in fact may yield better results than just trying to target the best places. So I'm going to give a real life example. I mean, we are dealing with a situation where research grants, for example, the research grants are being granted by boards or these committees that they look at the application, and then they score them, and they give these grants to the people with the highest score. So you can think of this highest score as the average, you know, that's the expected value. But then there are people who have some, not as much output, but some really good work and some really bad work. Now, would you put, if someone has a high research output, many publications, none of them really bad, none of them really good, and then someone with one very good article and you know, not that many, but a few inconsequential articles. So which one would you give the money to? If the safe bet is, of course, the first one, because the metrics state that they are better researchers. However, if you're looking for the next breakthrough, which one has the higher probability of making an actual breakthrough? The one with the greater variance in quality of output, or the one with the higher average output? So, I mean, this goes to all sorts of places in life, and that's actually a very good question. And I think this is a very good question to illustrate that, is that risk is sometimes a good thing. If you study finance and theory of investment and those sort of things, then, you know, there's a thing called beta, which means, you know, it's how much of a systemic risk you assume. I'm not going to go into details. It's a pretty bad characterization of that, but yeah. And people are always looking for that alpha. So I heard this one guy who was teaching finance says, there's no alpha, there's only beta. Meaning that those people who do really well, make a killing, a lot of returns for their investment, actually just taking on more risk. Could be. Not going to say he's correct, and this is a claim that I heard. So this, I'm just saying that this idea of a greater variance being overlooked in our society, this is a fascinating topic. Okay, let's look at one other. I'm going to just switch again what I'm going to share. Then we are going to stop after one more question. Let's share this this question first. Okay. So here was a question. An aluminum. There are two schools of pronunciation and writing even. Do you say aluminum or aluminium? It seems that I have chosen aluminum, but I think aluminium is, it doesn't really matter. Aluminium plate, yeah, it's British. Aluminium is British, and aluminum is probably the US way of saying. Doesn't matter. You get the point. So if you're British and offended by my use of aluminum, I'm really sorry. So let's say that we have a plate that is 4 millimeters thick, And it's used to make circular disks with diameter d, where this diameter is normally distributed with expected value 100 and standard deviation, variance 400. Meaning the standard deviation is the square root of that, so that the standard deviation is in fact 20. This is still ridiculous, because this would imply that there is a non-zero, albeit very small, probability of the diameter being negative. So here you see, it's 20 standard deviation. That's 5 standard deviations that's a 5 sigma event, and it's we'll see that shortly. But in normal distributions, that's extremely rare. But having said that, the approximation only works in the vicinity of this expected value. So it's pretty good for the expected value, yes, but if it's like this, it probably has a limit to it. So if there's a machine that cuts it and it seems to be making a normal distribution, there's probably some range of parameters for this machine, that cutting machine, that limits it. So it's not actually normally distributed, because it doesn't have a small probability of cutting, a kilometer range there. The probability of that would be really, really small, of course, in normal distribution, but it's still non-zero and also negative. I mean, it's obviously, the smallest thing you can cut is, not cut at all. It can't be smaller than that. But let's work with that. What is the proportion of the discs weighing between 50 and 100 grams? So 50 being about 2.5 standard deviation. No, sorry, we have to calculate this weight of the disk. So I have an example model answer in Finnish. So I'm sorry about the text being in Finnish, but we can still follow that, I think. So let's go there. So here we have it. The mass, well, it's 4 millimeters thick. We calculate this in grams because this density is 2,700 kilograms per per cubic meter. So per cubic millimeter, that's 1/10⁹ multiplier to that. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, so that's 8, 9 because it's grams. Yeah, so that's 1 cubic millimeter weighs 0.0027 grams. So that's 1 kilogram divided by 10 to the 9. All right. The mass we can then get by multiplying this. We calculate this in millimeters. The diameter over 2, that's the radius, to this 2 times pi, that's the area of the disk, times 4, which is the thickness of the disk, times 0.0027, which is the density. So a mass, given d, a mass has a disk has this mass. So we need to calculate this in order to get the range where this d needs to be. So there are two, look here. We multiplied, divide all these by pi times 0.027. So we get roughly these at the ranges. And then because this is d squared, then either this is between, we take the square root of that and the square root of that, or the positive or the negative. So we get two possible results. There are the cases where d is positive and the cases where d is negative. And we're going to eliminate this and assume that this is 0. Actually, this is not correct, technically. If we assumed that d is normally distributed, then this would have a very small but still non-zero probability. But we are going to assume that it's 0. It's so small and it's physically impossible, so we're going to eliminate this diameter being negative. So then we calculate this probability, where we just solve this for the d being in that region. We normalize both sides, so we get here the lower limit being 0.43 and the lower limit being minus 1.16 and the lower upper limit being 0.43. So minus 1.16. So here we have the cumulative distribution. We should get the cumulative distribution function at the upper limit minus the cumulative distribution function at the lower limit. The lower limit is negative, so we calculate it because of symmetry at this 1 minus and then this, the negative of that. And we can consult the tables or software to get this result, and we get 0.5434. So that's a slightly over 1/2 probability of getting this range of mass. The B question was, what is the expected mass of those disks? The thing about this is that we know that this was a kind of like a trick question. The variance can be gained by the expected value of d squared minus the expected value of d squared. And here we get the expected value of d squared as the variance plus the square of the expected value of d, which is handy because now we can use linearity of the expected value so that this is the mass. So the expected value of the mass we can get by the multiplier for the mass and then the expected value of d squared. And we can get that d squared by adding the variance and the square of the expected value of the diameter, and give us at 88.2 grams. So this I liked this question because here we can make use of the formula for variance in a reverse manner. Solve the expected value of d squared knowing that we know the variance. It's not uncommon for variables, normally distributed variables to appear in calculations in such a way that you need the expected value of the square. It's not uncommon at all. Very often we have some measure that is normally distributed and we need to calculate its square. It's definitely something that is useful. So remember that when you have a formula, you can always use it in ways other than you are used to. So very often the case is that you are used to calculating the variance using the fact that you can calculate ED squared minus ED, well, the square of ED. But here, in order to get the ED squared, you already know the variance and the ED, so you can calculate the expected value of d squared using those. So it's just a reminder that it's one of the great beauty and usefulness of mathematics is that if you establish an equality or a formula like this that it establishes that some quantities are equal, then any one of those can be solved if you know the others. So that's really it's a very powerful tool, one that we don't always appreciate. Maybe the main reason that mathematics is so useful. All right. So the only guest we now have is Alex. And if you have, Alex, any wishes of any questions that you'd like for us to cover. No, none yet. No news about the exam. I'll have to, next week, I'll consult with my colleagues about how we will do that. Or, well, to be honest, I'll consult my colleagues on how they are going to do that. And then I'm going to be shamelessly just replicating whatever it is that they do but in English. Because I don't want to, I'm not going to lie. I'm not very good with these tools and these technologies. I'm more of an old school kind of a teacher. So I'm just gonna have to wing it and take my cues from those who know what they're doing, or at least those who act like they know what they're doing. I don't have the I don't have the chutzpah to act like I know what I'm doing. So I'm just going to just shamelessly copy what those people do, and you know, if they make a mistake, then luckily, well, if I'm lucky, then maybe I will learn from those mistakes before I implement them myself. So not always going to happen. You probably noticed that I do a lot of mistakes here. So any other things that on your mind there? All right. All right. Yeah. Have a good day for you too. And I'm really glad that you showed up. I mean, I think I kind of blew this in the sense that I had just mentioned in the lecture that we're going to have this at 9 o'clock, and it seems that you know, I forgot to send the message. I had actually written the message, but I had just forgotten to send it. That's yeah. Huba Borkrind. That's what happens with. All right. Have a nice weekend to you. I wish everyone who's watching this after the fact that, you know, you got something out of this. Next session will be on Monday at 2 p.m. as scheduled. We'll have everything that used to be at 8 o'clock. We'll have them in the next couple of weeks. We have them at 9 o'clock instead of 8 o'clock. But I'm not going to change the schedule too much because other people are having their lectures at the allocated time. But I also know that if I have it at 8 o'clock, then no one is going to show up. So if you're watching this, it's going to be 9 o'clock if the schedule says 8 o'clock. Otherwise, it's on schedule. All right? So Tuesday, 10 o'clock, Wednesday, 9 o'clock, Monday, 2 o'clock, and Friday, 9 o'clock. All right. Stay safe, people. Stay indoors or out of crowds at least. And I'll see you next week. Bye.